Yeah, but I cannot find the edit solution for. Yeah, it's a bit strange. Yeah.
Yeah, you can start now. See?
Okay. Yep.
Yeah.
Wait a minute. Yeah, I just text you because I cannot find the edit option in my console. So maybe you can help me to change the name a bit. Yeah. I send you a message there. Okay, so I will go ahead. So hello everyone. So welcome to this webinar. Actually, it's a joint event between the Atchbury collection expert and also the Atchbury the YP talk, right, provided by the Atchbury Denmark YP group. So today we are very happy to have Dr. Lily here. So let me briefly introduce Dr. Lee. So he is a senior lecturer and ARC the Decker Fellow 2020 in the Faculty of Information Technology, Monash University. And prior to joining the Monash, he was a research associate in software engineering at the University of Luxembourg and an honorary research associate at the University College London. Okay, and he obtained his PhD in November 2016 from the University of Luxembourg. And his research interests are in the areas of Android security, static analysis, machine learning, deep learning, and empirical study. Okay, so let's welcome Lee for today's topic. So the topic is towards engineering high quality and secure mobile apps for the social good. Okay, so let's welcome Dr. Lee. Yeah, then I hand it to you.
Yeah, thank you, Weizhi, for the invitation and for the nice introduction. And good day, everyone. Thank you for attending this webinar. My name is Li. I'm currently a senior lecturer at Monash University. And I'm really honored to be invited to give this talk about my recent research. I'd help the community engineering high quality and secure mobile apps for social goods. So before going to the details, let me first briefly introduce about Monash University, in case you have not heard about it before. So Monash University is named after Sir John Monash, who is a famous Australian, contributed to almost every level of Australian life. So in recognize his contribution, his portrait has hence been put on the Australian $100 note. And Monash University is a research-intensive university, striving to achieve excellent education and research in Australia, as well as across the world. And it has been constantly ranked as the top 70 universities in the world. And as shown in the bottom two figures, Monash University is located in Victoria, and particularly on the southeast side of the capital city of Victoria called Melbourne. And as you can see in the right bottom figure, Melbourne City has a very long beach side and also surrounded by a large green area, making it definitely a great place to live and to visit. So speak of that, if you are interested in visiting Melbourne or Monash University, please come. But certainly not now, as we are still in lockdown, unfortunately. Actually, today, it marks Melbourne, the city, to endure the world's longest lockdown with 235 days already. And probably there's still 1 month or 2 months to go. Yeah, so also before going to the technical details, I would like to emphasize that the content I'm going to share in this talk is not my personal contribution, but certainly the collaborative efforts and specifically including the contributions of my two former PhD students, Jun and Ping Fan, co-supervised with Professor Jack Klein at University of Luxembourg, as well as my current Monash SMART team, including Dr. Xiao Chen, and as well as my PhD students here. So the title, the talk I want to share today is called Towards Engineering, High Quality and Secure Mobile Apps for Social Good. Let me first start to explain some of the keywords in the title. So the first keyword is mobile apps. So why should we focus on, why are we focused on mobile apps? As you have already know, that our world is going more mobile, with probably everyone has access to some kinds of mobile devices. And I guess in the audience here, everyone probably has a smartphone. And also the revenue of the mobile ecosystem has continuously growing as well. As shown in this figure, like in 2020, mobile ecosystem, the revenue of mobile ecosystem has exceeded $4 trillion US dollars. So what does $4 trillion US dollars means? It's just a number, right? Here, let me make a simple comparison. The GDP of Australia in 2019 is just 1.3 trillion, which is not even half of the revenue of the mobile ecosystem. So such a large, huge revenue creates a lot of opportunities for either developers or users, as well as for many malicious people who may take advantage of this huge market, huge ecosystem here. And even in the academic side, although Android is just introduced like 10 years, roughly 10 years ago, and there are already more than 6,000 papers published based on the DBLP search. I did it today with Android as the keyword. So like Android showing in the title of all the papers. 6,000 is really a lot, yeah, which makes Android a very hot topic in this domain. And it was also interesting to say that my PhD supervisor, Professor Jack Klein, is ranked as the second contributor in this domain. So that's the first keyword I want to share is the mobile apps. And the second keyword I want to share is social good. The term which often refers to actions to put human values at the forefront while improving the software systems, like in our case, it's for mobile app ecosystems, including the apps design, development, testing, maintenance, and all the life cycles in software engineering. And particularly, it involves a lot of stakeholders in the ecosystem, including developers, as well as the official Android framework developers, as well as the third-party library developers that the app developers rely them to implement mobile apps. The developers also access to many like code repositories and question-answer websites to implement their apps. And after completing the apps, developers may release their apps through some app markets, such as the official Google Play Store, to distribute the apps to end users. And end users can use the apps as well as give feedbacks through the inside the ecosystem. So when we talk about the social goods, we want to invent approaches to benefit all of them in the ecosystem. And at Monash University, we have a specific dedicated lab called Humanized Lab, led by ARC Laurent Fellow, Professor John Grundy. And the Humanized Lab aims at incorporating the unique and varied aspects of people's needs and abilities to software engineering practices. And with John Grundy, we have actually secured an ARC discovery project entitled Values-Oriented Defect Fixing for Mobile Software Applications. So we have looked at various different kinds of human values in this direction. One of the examples that we have shared is published at this year's ICSA conference. If you are interested, you can take a look. So that's the second keyword I'm sharing. The next keywords I want to share in the title to help you understand the background of the talk is high quality and secure. And I guess it is not uncommon to say this kind of error messages when using mobile apps. Like some apps is stopped running or crashed, or even to show the different security messages around the web, right? So actually, there are a bunch of this kind of quality and security issues happening in the mobile ecosystem every day. To cope with that, our community has also invented various approaches to help developers and users mitigate them. And to the best of my knowledge, those approaches generally take three types of techniques, being the static analysis, dynamic analysis, and machine learning, deep learning based approaches. So now let me first briefly introduce what these three techniques mean. Right. So static analysis generally means to look at the software artifacts statically without actually running the code. Like take a very simple example. The static analysis approach might read Android bytecode and then mining into the code to make connections between the different code artifacts, such as method to build core graphs, for example, and then based on this graph to generate some results. If you want to know more about static analysis of Android apps, I highly recommend to read out our systematic literature review paper. And for dynamic analysis, which are sometimes also known as dynamic testing, which mainly aims at to really testing the app. The simple methodology of dynamic testing involves installing an app to a real device and then generate some test cases and send those test cases to actually run the app under test. And then it attempts to observe the execution behaviors of the apps under testing, and finally clean the environment to obtain the testing results. There is also a literature review detailing the different the works done in automated testing of Android apps. So the final approach is it's a very hot topic in recent days. It's called machine learning and deep learning based approaches. The machine learning techniques in the mobile domain are mainly proposed to detect malwares or malicious behaviors in Android apps. So the idea is quite straightforward. It starts by extracting some features from given Android apps, and then leveraging classifiers to differentiate malicious apps from benign ones. And this literature review paper also detailed the recent works in this direction. If you want to know more, please have a look. So today, I'm not going to detail this literature review, so what happened in the state of the art, but instead I want to share some of the actual technical works we have done, contributed in this domain to help developers and users mitigate the quality and security issues. So specifically, our research leveraging the three types of techniques aiming at to solve problems in two research directions. One is called the app quality assurance. So another one is called the app security, right? And the different problems we are targeting, including, for example, compatibility issues, the inaccessible and duplicated APIs, etc., and many others like privacy leaks detection, repackaged Android, repackaged app analysis, as well as robust machine learning analysis. So now because of time limits, I'm not going to detail every problem we have resolved. I will try to highlight one from each direction. But if you are interested in some of the researchers mentioned here, please don't hesitate to contact us. We really appreciate your contact, and we're happy to collaborate with you to resolve some of the issues here. So for the first work I would like to share is the privacy leaks detection work in the mobile app security direction. So in 2014, some of the background about privacy leaks detection, which has been a very hot topic in the mobile domain, right? So in 2014, Professor Eric Borden, now at the University of Paderborn, and his teams has released a research tool called Droids, which aims at performing time analysis to detect privacy leaks in Android apps. So the Droids tools is actually made open source on GitHub. And as you can see that the Droids tools has now received more than 500 stars and exceeded like over 200 foxes. So it's really a successful tool and very popular tools to detect the privacy leaks in Android apps. And the idea of the Droids tools essentially want to uncovering the privacy leaks by static time analysis. So static time analysis is a very straightforward technique. Let's take the following figure as an example. So the static time analysis starts by defining some source and sink points in the program, where the source points mainly means that somewhere some sensitive information will be obtained from the software artifacts, while the sink point indicates some dangerous behaviors, such as sending some information to a remote server, for example, right? And then the static time analysis starts by countering the source points, and then track the flow of those data, counter data, to say if some of the counter data will eventually reach some sink points. If there is a path identified between a source point and a sink point, then they say there is a sensitive data flow, and thus a privacy leak possible. So in the Android app analysis domain, so the idea is given Android app, it first it's going to build a core graph, and then traverse the core graph to find such sensitive data flow. The basic idea of Droids is quite straightforward. But here, the most important things in this work is to build a sound core graph, because Android apps has some specific features that keeps it from achieving that. Today, I'm going to share two of such features. The first one is called the Intercomponent Communication feature. Another one is called the Java reflection feature. So intercomponent communication is the basic communication mechanism introduced by Android. Let's make a very simple example to illustrate it. Let's assume that the rectangle here is an Android app. And this Android app is made up of two components, specifically activity A and activity B, right? And these two components can communicate with each other through the so-called intercomponent communication method, or ICC method in short. Like in this example, the start activity method, right? But actually, the actual communication of these two components is through the Android framework. The code is outside of the Android app itself. So that means if we analyzing the Android app alone, the communication between the two components, the information is missing. So in other words, if we launch Droids on this simple tool, involving intercomponent communication. Droid will build 2 independent core graphs, one for each component, and then generate partial results. But what we want here is intercomponent sensitive data flow, right? Or in other words, what we want to achieve is we want to build a intercomponent core graph, and then to get the actual results we want to achieve. We have hence extend Droid to implement a tool called ICTA, which takes mainly 2 modules to achieve the purpose by first inferring the possible intercomponent communication links in the Android apps. We achieve this by performing the backward constant stream propagation analysis to find all the possible values specifying how the SAC communication is done here. And then, like for example, this constant stream propagation will allow us to build a link like activity A. Statically, activity A is going to communicate with activity B. And after that, we artificially enhance the traditional core graphs to build intercomponent core graphs, so as to support Droid to build intercomponent sensitive to support Droid to detect intercomponent privacy leaks. So that's the first work we introduced to the community through handling the intercomponent communication for detecting privacy leaks. So there is another feature called the Java reflection, which can be used to access some code outside of the Android boundary as well. So it's like some external code. And the Java reflection is a very basic feature. Some example of Java reflection is showing here, very simple examples, like the code in the reflection code could just like say dot new instance, which actually means is the red code behind is to initialize another class here, and the reflectively called invoke method is actually stands for another method. Like in this example, a very simple example is called like set IMEI, for example, right? So when directly analyzing the code involving reflective calls, there will be a problem between the different contexts, like the original context of the application code is not connected with the reflectively accessed context. So it will also cause problems when build the core graph. So to mitigate this problem, we introduced a tool to the community called Droids, which in the first step, trying to infer the target values of the reflective calls through the backward constant stream propagation as well. So in the first step, after scanning the code with backward analysis, we want to know that what does the reflective calls actually mean, right? If we can statically collect such information, in the next step, we could replace the reflective calls with the actual method it means to call. That means we replace reflective calls with traditional Java calls. So as that, for example, after this handling, Droid could directly perform reflection-aware static analysis, right? This figure shows actually an example we obtained, like which is a core graph example from the app. Here, the black points shows the original methods that involved in the core graph, while the green and the red points are those methods that actually accessed through reflection. So when we tackled the reflection problem, we could enlarge the core graphs. As you can see, there are many nodes in green and red added to the core graphs. And also that the rate points actually measure access to some dangerous behaviors, which are protected by permissions in the Android system, which shows that reflection is not only difficult for static analysis approaches to handle. Reflections could also be leveraged by the malicious people to hide some sensitive operations. So which shows that there is a need to perform reflection-aware analysis, especially when in detecting privacy leaks in Android apps. So that's our contribution in the privacy leaks detection domain. And recently, actually, we found that when we talk about the sensitive data flows, the sensitive informations in Android may not always return from some methods or, let's say, Android APIs. It could also be some sensitive fields, especially the sensor data in the Android device, mostly provided through some specific Android fields, class fields, not methods, right? But unfortunately, FlowJoule does not support to perform such timed flow analysis sourced from some fields. So we also contributed a pull request to FlowJoule to support field as source to do the timed analysis. And this pull request has already been merged into FlowJoule. And also our previous intercomponent communication contributions is also currently merged into the FlowJoule tools, which has been already used by many researchers, even industry companies in the domain. And actually, we have going beyond the field-based sources to release a tool called Secure, aiming at categorizing sensor leaks in Android apps. So, which not only involves field-based timed analysis, and also we need to identify which sensor will leak the information to make that a connection. I'm not going to get to the details of this work. If you are interested, you could read our paper, which will be presented at E3 this year. So that's the first work I want to share. It's about privacy leaks detection. The second work I would like to share today is in the app quality assurance research direction. It's called mainly the compatibility issues. In dictionary, compatibility is often means a state in which two things are able to exist or occur together without problems or conflict, which in Android it means if there is compatibility, the compatibility means that the apps can be run on Android devices, but compatibility issues means that they cannot run, right? So, for example, when some of you, if you are Android users, you may encounter this issue when you try to install some apps from Google Play, right? They say that this app is not compatible with your device, which is very frustrating because you want to use the app, but it does not allow you to use it. And more specifically, in this work, we have identified two types of compatibility issues. One is called forward compatibility. Another one is called backward compatibility. Let me use this very concrete example to explain why the preference is introduced here. So in this example, it includes two apps, App 1 and App 2. So App 1 is developed targeting the Android system API level 19, right? While the App 2 is developed targeting the system API level 22. And there is API called API 1, just deleted after the system API level 19, while API 2 is just introduced in the API level 22, right? And suppose I'm the poor person, has a smartphone running the Android API level 21, and I want to use these two apps. So what will happen? Which will most likely that both of the apps cannot be running on my device. Both of them will crash because API 1 and API 2 are not available in my device, right? Because they are either being deleted before or introduced later. So that's the compatibility issues we are mentioning here in this work. And to tackle this problem, we designed and implemented a tool called SAID to automatically detect the compatibility issues in the bytecode version of Android apps. The SAID tools mainly takes 3 modules to achieve its purpose. So the first module is called the API lifecycle modeling. So in Android, the Android framework has been regularly releasing new versions, like and each version is named after a candy. At least for the most previous versions. Like in each version, they might delete some APIs, also introduce some new APIs, right? So what we propose to do in the first module is to directly analyze the Android framework source code hosted on GitHub. And we compare all the major releases of the Android framework source code, trying to identify, to model each API when it is introduced to the framework and when it is removed. Right. After this step, we could build a mapping, something like showing in the bottom, like the life cycle, the ranges for each API. And in the second module, which takes as input the Android bytecode APKs, trying to extract all the APIs used by this app. And here we also need to take into account the dynamically loaded codes. As we mentioned before, Android apps may use reflection and dynamically code loading to access some external code. Those code could be also introduce compatibility issues. So we have to also consider them. And also, Google somehow knows that their system and the whole Android ecosystem is hugely fragmented. So they have introduced the mechanisms to mitigate the compatibility issues in the ecosystem through the so-called protection mechanism. A simple example is shown in the bottom of this slide. It's like they recommend the developers to actually check the current SDK versions running on the devices. Like in this example, only if the app is running on a device with the API level higher or equal to 11, and then the following API will be excluded. Otherwise, the problematic API will not be excluded. So we want to make sure that those protections will be recognized so that we will not report some compatibility issues which are not actually protected. Or in other words, there's no such compatibility issues. So we achieve this by building the so-called conditional core graph. So we try to add the different checks on the traditional core graph to handle the various protections. And then in the last module, we just compare the extracted, the actually used APIs in the APK against the lifecycle model we built from the Android framework source code to identify the issues. There is also a small issue that we realized later, which is that the Android source code, which is written in Java, there are some advanced Java features such as the generic programming and the var argues, for which the definition of those methods in the source code version is different from the actual version written in the bytecode. But once we identify those features, which are straightforward to change them to make the exact match. So after we implement these tools, we have conducted extensive experiments to evaluate its effectiveness. And we also trying to analyze some of the top open source Android apps. And we, if we identify the compatibility issues, we will we then submit those issues as problems to those open source source projects. And I think this result is just within 2 days that several of the project developers already confirmed that the submitted compatibility issues are correct, and they are happy to fix them in a short time. So this experiment shows that SAID can indeed provide helpful information for developers to quickly understand, evaluate, and eventually fix compatibility issues. So in more recently, in line with this research direction, we further conduct a literature review about compatibility issues in Android apps because this topic has become quite hot in recent years. And our review have found that at least for the API-induced compatibility issues, there are at least 5 types of issues, including the evolution-induced, as well as the device-specific because of the customizations done by different Android manufacturers. Like, let's say Samsung might customize their official Android framework to align with its own features. So it will also introduce compatibility issues there. So our original SAID tools, unfortunately, can only handle the first issue here is the evolution-induced method type of errors. So we take additional efforts here to also to extend the SAID to also include all the other types of issues we identified through the literature review. We later also further realized that it is not only important to statically detect those compatibility issues. It would be also great to dynamically confirm those issues through dynamic analysis, and also eventually to automatically repair those issues. To this end, we have implement and made available to the community online service called App Scanner. You can access App Scanner through the URL showing in this slide. And you can upload some APKs and wait a little bit. If it contains compatibility issues, App Scanner will tell you what kind of issues it may contain. And the App Scanner uses the latest SAID version, which includes all the 5 types of compatibility issues we identified through the literature review already. And then in the next step, we want to confirm those issues statically detected. So we introduced a lightweight crowdsourced testing platform called the Lazy Cow, which trying to distribute some compatibility issues related to test cases, which are very small. So that we will avoid some bandwidth problems when for the crowdsourced testing. And we have tested our approach on some of the devices, and we would hope that other platform and the tools can be tested over the various Android devices available in the world. So if you are Android device users, you are more than welcome to help us do the test by download the Lazy Cow app through this slide. And you can also access this page in the App Scanner website. So after we detected statically detect the compatibility issues, And hopefully most of them could be confirmed. Actually, by running them on actual devices, the next step we want to achieve is to help users and developers automatically fix those compatibility issues, right? So we believe it is not only important to help developers repair such issues at the development time. For example, through some IDE plugins, which we are currently working on. We also believe that it is important to repair them on the fly, meaning that when the users are using the apps, if there are compatibility issues, we would like to directly repair them so that the users can still use the app instead of encounter a crash or the compatibility issue, which is really user unfriendly, right? So for the latter case, we have actually designed and implemented a tool called Repair Droids, which aims to automatically repair compatibility issues for published Android apps. The implementation of the tools includes also 3 modules. I will just briefly introduce them. So the first module, because we know we already detect some compatibility issues, actually hundreds of compatibility issues already. So we manually understand them and then introduced templates to model those issues. And then we leverage static analysis to actually read the templates and for given published Android apps to locate where the compatibility issues locate, and eventually applying the templates, the patch to fix the compatibility issues directly for bytecode Android apps versions, the published Android apps. Not that we don't require the source code in this world. And it is worth highlighting that this work. We have introduced the templates that allows the users to use the whole language called the Jimpo to write the patches. So the Jimpo is the default intermediate representation of Shoot. Where Shoot is a popular Java static analyzer framework. So because we allow the users to use the whole functions of Jimpo to freely write their patch, so we believe our templates really generic and flexible, can be used to represent almost all the types of fixes for compatibility issues. I mean, not even compatibility issues, but also other types of issues. But we haven't explored that, but we believe it could be also applicable. We will open source our Repair Droid tools very soon. Please look around. And so in this talk, I have mainly talked about the methodologies that our fellow researchers as well as our research teams applied to tackle the various mobile problems. So the straight techniques, static analysis, dynamic analysis, as well as the machine learning and deep learning based approaches. And we talk about the 2 main research directions handled in this in our work is the app quality assurance and mobile app security. And for each of the direction, I detailed the one particular problem, which is compatibility issues and privacy leaks detection. Right. So because of the time limitations, I'm not going to detail the other problems we have handled in the journey of taking, fixing or analyzing mobile apps. So to conclude, we are still trying to achieve our objective, which is towards engineering high quality and secure mobile apps for social good. And if you are interested in this objective and you want to join us to work together, you are more than welcome. And with this, I would like to end my talk and open for questions and suggestions. Thank you.
Okay, thank you very much for Dr. Lee. Yep, the talk is very interesting. And I can see there is one question in the chat is that, can you share the slides after the webinar, or you can make it maybe available?
Yes, sure. I can definitely share the slides. I don't know if the host have some channels to share. If not, I can definitely put the slides on my personal page. Or if you send me an email, I will be happy to reply with the slides.
Yep, that's great.
Yeah.
Okay, yeah. Ali, can you check any questions from other channel? Do we have any questions there? Ah, okay. Because Ali's not here. So yeah, so I have a very maybe a simple question is about, because the topic today is about high quality and the secure apps. Then how to define a high quality app? Because for example, the goals or some criteria or requirements that we need to consider. So we can consider it's a high quality app.
Yeah. So yeah, very good question. So to be honestly, to me there is no really criteria to define high quality and secure apps. So in my mind, or in my research teams, we're just trying to do as much as possible to fix quality issues as well as fix security issues. So this is the object of us, is to achieve high quality and secure mobile apps. So in practice, we would say just say if we can mitigate as much as possible such issues, then it would be great already.
Okay, thanks. And also because we observed that also there are some new platform like the Hormone OS. So do you have the future plan on these platforms or not?
Yeah, definitely. We have already looked into some of the problems on Hormone already. Yeah.
Okay. Yes, thank you very much, Dr. Lee. As okay, because Ali is not here, and so I cannot check the questions from the streaming channel. So is there any other question from our audience? So you can write down your question, right? Or of course you can contact Dr. Lee, right, later, because the email address just shown on the screen, so you can just contact our speaker. Okay.
Yeah, sure. Yeah.
Yes. Then if there's no other questions, so let's welcome Dr. Lee for this wonderful talk again. Okay, thank you very much. Okay, and if you have any question, please remember to send your question directly to the email address. Okay, so thank you very much
Sure.
for the time and for the talk. Okay, thank you very much.
Yeah. Thank you, Weizhi, again for the invitation and for host the webinar, and thank you everyone for attending this webinar. Looking forward to receive your questions and suggestions.
And looking forward to see you maybe physically, right, in near future. So we are open again.
Yeah, sure. I'm definitely interested in traveling, as I introduced before. We have enough lockdowns in Melbourne.
Yeah. Yes, of course. People really need some travel, right, and take some holidays, right, outside, right? Yeah, so it's very important. So
sure.
Hope so. Okay, thank you again. Yes.
Yeah,
so
thank
have
you.
A good day.
Yeah, bye.
Yeah, have a good day.
Yeah,
Bye.
you too. Bye.
Bye.
Bye, everyone.
See you.